Hello everyone, my name is Ryan Beams and I'm from the Food and Drug Administration. I'm going to be talking to you today about some work we've been doing on the angular dependence of spatial resolution in virtual reality displays. And this work was done with Brandon Collins, Andrea Kim, and Aldo Badano. First, just a disclaimer of the mention of any commercial products during this presentation. So a common question I get from people when I mention that I'm at the FDA and we're doing research on augmented and virtual reality is, why is the FDA interested in working in this space? And one way you can think about that is considering the wide range of applications that exist for AR and VR devices. The most obvious, of course, being entertainment, but it's also being used extensively for training, education, teleconferencing, remote control, and another interesting one is data visualization. And you can think about how you could take any of these applications and translate them into the medical profession. Or instead, we're looking at training and simulations, education. Telemedicine is an interesting one where you could have medical professionals in remote locations interacting with each other, potentially with patients, and with the same medical data. Remote surgery is also another exciting application for these technologies. And then data visualization as well, because you can take these already three-dimensional medical images and then open up new possibilities for how doctors can interact with them to understand them in a more intuitive way. And this is being explored for diagnostics and surgery planning. And then finally, entertainment can actually be translated almost directly for applications such as pain management and other therapeutic applications. So because of the wide range in medical applications, and all of these have their own challenges to them, we recently hosted a public workshop, and the goal of this public workshop was to get the stakeholders from all the different arenas, so academics, government, medical professionals, industry, both on the device development and on the application development, into one location to discuss what are the challenges in using these technologies for virtual and augmented reality. And this entire workshop will be available to the public, so if you missed it and you'd like to listen to it, I invite you to do that once the link is live. And as a part of that, we also had some very nice panel discussions about what are the methods and ways to go forward with this effort. Within the FDA, in the science and engineering laboratories, we have a medical extended reality research program. And as a part of this program, we are looking at a number of different topics, including color rendering and understanding how the pipeline impacts an input medical image compared to what the final user sees. Also characterizing the optical performance, such as the eye box and how you mount the headset on your head, chromatic aberrations, contrast, and then resolution, which I'll spend my time talking about during this presentation. And then finally, at the end, these devices have to go onto the user, and so we're also looking at human factors issues such as motion tracking in AR surgery. Okay, so now to get kind of to the important point of this presentation, I want to talk about the resolution dependence across the field of view. So if we think about starting with some initial image, in this case I've taken digital pathology as an example. This could be surgery planning, could be a wide range of images. And if we have this image on a conventional display, the resolution, regardless of where you look on the image, is going to be fairly consistent. So if we look in the center versus over on the right side, resolution still looks good and as you would expect. That's not necessarily the case when you move to a head-mounted display, however, because there's additional optics that are in there as well that can impact the contrast, color performance, resolution, among other things. So if we look at this same patch on the head-mounted display, you notice the resolution's actually dropped off quite significantly. We've also looked at this in terms of contrast. So if we start with looking over a 30-degree field of view of the head-mounted display and look at the percent contrast, as you start to go to higher resolution features, the contrast starts to drop off fairly quickly. And so it really illustrates that where you are in the field of view and the frequencies, the spatial frequencies of the content, impacts the final result. Okay, so now that we agree that where you are in the field of view is important, we should probably go about measuring that. Well, what would be the best way to do that? So if we think about this simple cartoon of how a human looking at this head-mounted display, and they have some field of view for each eye. So we could just replace the eye with a camera, and this would be great because it's a fast measurement, single measurement, it's easy. But one problem is it's not how the eye works, because the camera system has a fairly consistent resolution over the entire field of view, whereas the eye does not. So this is looking at the distribution of rods and cones across the eye, and of course the eye has a fairly narrow region called the fovea that has high resolution, and to make a two-dimensional image, the eye scans across it. So an alternative way to take these measurements is to do an angle scanning approach that more closely mimics the human eye, but it comes, of course, at the cost of being slower and requiring scan stages. Now, even if we agree at this point that we should do an angle scanning method because that more closely agrees with the human eye, the problem is still not solved. And this has been a discussion topic in IEC about even if you're going to do a rotation, what's the point at which you rotate? So the two different approaches are an eye rotation versus a pupil rotation. The eye rotation is what we biologically do, where we have a center point and the eye moves up and down. One thing to note is as the eye does that, the pupil moves off of this optical axis. Whereas if you do a pupil rotation, you keep the pupil fixed on the optical axis, but the eye is actually rotating out of its socket. And while this may seem like a small difference, there's a recent paper by John Pensick exploring these differences in the case of distortion. What you actually see is the pupil rotation in red versus eye rotation in green. You actually get fairly different results. And so this really illustrates that if you go about measuring some of the properties of these head-mounted displays, you have to think very carefully about how you go about measuring. Okay, so the focus of this talk, though, is resolution, and we also need to think about how we measure that. Now, a common approach for measuring camera systems is to do a slanted edge test, but this is actually kind of difficult for displays, and particularly head-mounted displays, because there's a subpixel pattern. So our slanted edge is going to cut across those subpixels, and then the profile of that edge is suddenly going to become quite complicated. Alternative method that we decided to use is look at the line spread response, where we have turned on a single line of pixels, and then you can measure the width of that, and then use that to determine what the resolution is of your system. In the laboratory, the way this looks is we have a imaging system with a CMOS sensor, a lens in front, and then we put the pupil out in front of the lens to more closely mimic the human eye. And then in the wide field case, the pupil's fixed, we just image it onto the sensor. In the angle scanning method, however, we're rotating the pupil of the camera, and so the bundle of arrays that we're collecting and mapping onto that CMOS sensor is different, and that's going to impact the final measurement and final image that we get out of the system. The way this looks in the lab is we have our head-mounted display with a camera on an XYZ theta stage. It's fairly straightforward. Okay, so if we then set this up, go in the lab, start taking measurements, and we start in the center of the field of view with our line spread response. We want to look at this single white line of pixels. You can nicely see the subpixel pattern. You can shown here in the zoom in, and then to maybe get a little bit better feel for what's going on, you can also look at just say the green subpixels, and we get a really nice symmetric shape out, which is what we would hope for. However, if we go off the center of the field of view to say plus minus 10 degrees, for both the eye rotation case and the wide field case, we start to have a fairly large decrease in resolution. We get this separation of the colors and this kind of rainbowing effect. And if we look at just the green subpixels, you get this kind of comet shape. And it's more significant for the eye rotation case than the wide field. And the reason this happens is due to the aberrations of the lens. And so one example of that's the chromatic aberration, but there's other ones that are also coming into play here to impact what the final image that you get out as you go across the field of view. So then to make this a little more quantitative, we can perform these line spread response measurements across the field of view of the display. And so in this case, we're just looking from -15 to +15 degrees. That's along the horizontal axis. And then the line spread response is along the vertical. And so what we find is that in the center, the resolution is the best, and then it starts to decrease as you go away from the center of the field of view. And that's the case for both the eye rotation and the wide field case. And then you can look at the line spread response profiles, and again, you see as you go off axis, it starts to decrease in signal strength and the width gets wider. So one thing we decided to do with this was to compare how the Vive and Vive Pro looked for these same measurements. And the reason for doing that is the design is quite similar, but one has more pixels than the other. So it allows you to ask the question, how much does it really help you to add more pixels to the display? And what we see is that we get similar kind of effects with this fanning of the resolution. And then in the center, the resolution is in fact better, but it doesn't necessarily help you too much as you go off axis. Another way to consider how the resolution is changing is we can do the change the line spread response into the modulation transfer function, and you can think about the modulation transfer function as being the filter function for the optical system. So if we start with our impulse response or line that we send in, we get some line spread response out. We take the Fourier transform of that to get the modulation transfer function where it's spatial frequency versus percent contrast. For a lower resolution system, we have a wider line spread response, and then the modulation transfer function drops off faster, meaning that the cutoff frequency is lower. Another thing we can do with this is we can look at the 50% contrast point and what spatial frequency that corresponds to. So for the Vive and Vive Pro, using the two different methods, these are the results for the modulation transfer function. You can see the Vive Pro has a higher spatial frequency cutoff than the Vive, which you would expect, and the eye rotation drops off faster than the wide field method. And as a reference, here's the modulation transfer function of our camera system. So as I mentioned on the previous slide, you can also take all this data and kind of compress it down by looking at the 50% contrast level. So that's what we've done here. So this is the spatial frequency at where the MTF equals 0.5. Along the horizontal is the angle in the field of view. The red lines show the Vive Pro and the blue shows the Vive. And so what you see in the center is that the Vive Pro has higher resolution than the Vive, which you would expect, but then as you go off axis by say 5-10 degrees, the performance of the two is actually quite similar. And then also importantly, the measurement method for the angle scanning drops off faster than the wide field approach. And then finally, the way we can compare these is look at the full width half max of the line spread response as a function of the angle in the field of view. And again, we see that we have this kind of narrow 10-degree window where the device performs quite well, and then it starts to drop off quite quickly in resolution, and it drops off much faster for the angle scanning method. And if you look at the percent difference between the two methods, it's say 15 degrees, it's around a 40% difference between the two methods. And this really illustrates that it's important to consider how you're going about measuring these devices. So with that, I would like to conclude. I've shown that the measurement method is very important to consider and can greatly affect the results. The wide field method tends to overestimate the resolution of the head-mounted display. And then finally, across the field of view, the optical performance and not the display limits the resolution, which is an important consideration for the rendering pipeline, as well as for applications where consistent image quality across the field of view is important, such as surgery planning or diagnostics. Finally, in future work, we're interested in applying this method to other subpixel patterns, as well as extending it to binocular measurements. So with that, I would like to thank you for your attention.